everyone. Welcome to this month's edition of our monthly talk. And let me start with the intro of the forum. Varahamira Science Forum was started by a group of amateurs with the intention of taking science, engineering, and technology to the common person in a language that is understandable to all. The stress is more on making the audience understand the topic and make them feel comfortable. We believe this works well when people tell a good story. So we welcome people from all walks of life who can tell a good story. And we have had professionals, amateurs, and even school kids talking to us, the last of which we want to make an annual occurrence once the pandemic settles down and allows some form of normalcy. So this is our story, and we started in August 2017, and we are in our 5th year of existence. Not bad for a set of people who want to talk, listen to science. Our sessions have all been online since April 2020. All our lectures are recorded and available on YouTube, and we have around 1.4K subscribers. We also have a WhatsApp group where we talk science, I should say. It sometimes get very heated up, but we do ensure that the focus is always on science, okay? And we are also on Facebook, Twitter, Instagram, and YouTube. These are our details, and you can follow us on Facebook or Twitter. And if you want to join our WhatsApp group, this is our contacts. You can reach out to any of these people. And more importantly, we also run classes on topics related to maths and astronomy. If you want to know more about those classes, you can reach out to one of these two people. And that brings us to today's session by Professor KP Mohanan, and I hand it over to RV to do the speaker introduction. Over to you.
Thank you. Yeah, thank you. Thank you, Ramanan. I'll read out a quick introduction of today's speaker, Professor KP Mohanan. Professor Mohanan studied at MIT, Cambridge, USA. He was working with Noam Chomsky and Morris Hale. He received his PhD in linguistics in the year 1982. Mohanan has made significant contributions to linguistics theory and has worked extensively on the nature of academic knowledge and inquiry against the backdrop of human beliefs. He taught at the University of Texas, Austin, University of Texas at Austin, MIT, Stanford University, and the National University of Singapore. Before returning to India in the year 2011, he joined the Indian Institute of Science Education and Research, ISER, Pune, from where he officially retired at the end of 2016, though he is not retired from the educational enterprises as yet. Along with Tara Mohanan, his life partner and colleague, he designed an inquiry-oriented undergraduate linguistics program at National University of Singapore. He was also the architect of the general education program at NUS. He is a co-founder of Think, spelled as THINQ, Think Education, a group of individuals dedicated to educating the mind, their own and that of others. Without further ado, I hand it over to Professor Mohanan for today's talk. Over to you, Mo.
Thank you. Thank you for giving me this opportunity. Let me begin by sharing the screen. Okay. Okay, this is the structure of the talk. It has two parts. In part one, I'll talk about scientific temper. What is scientific temper initially? And then I'll expand that idea to rational temper, which goes beyond science, and then to academic temper, connect that to academic knowledge and education. That's the first part. At the end of first part, I will take some questions, if there are quick questions, clarification, and so on. And then in part two, talk about different strands of academic temper, about 4 or 5 different strands. And at the end of each strand, I'll give after lots of examples. I'll again take questions after each strand. And then there'll be a short third part connecting all this to the enterprise of reforming curricula. So this is what the plan is going to be. So part 1, the ideas of scientific temper, rational temper, academic temper, and connection with academic knowledge and education. So let me begin with this quote. The true scientific temper is a modest, open-minded temper, a temper ever ready to welcome new light, new knowledge, new experiments, even when the results are unfavorable to the preconceived opinions and long-cherished theories. I would like to emphasize the second part, even when the results are unfavorable to preconceived opinions and long-cherished theories. This is the openness to self-correction as part of scientific temper. Another quote, this is from Bertrand Russell: critical, undogmatic receptiveness is the true attitude of science. All these words are critical, undogmatic, and receptiveness. They're all important in the characterization of scientific temper. So we may actually define scientific temper as the attitudes and predispositions resulting from the practice of scientific inquiry. This is what we have seen in actual education. If students are given an opportunity to engage in scientific inquiry, after a year or two, they develop different aspects of scientific temper effortlessly. It can come only through that practice. Okay, let me now connect scientific temper to the rational temper. Why am I doing this? Because science, by science, I mean physical sciences, biological sciences, and human sciences. I'm not going to make a distinction between physical sciences and biological sciences as sciences, and the so-called social sciences as not sciences. I include all of these, which is why I call it human sciences as opposed to social sciences. And there is another aspect that these are all collective rational inquiries: scientific inquiry, mathematical inquiry, philosophical inquiry. Rational inquiry is not restricted to science. It also includes mathematics and philosophy. So it is better to expand the notion of scientific temper as rational temper, which includes scientific temper. And we may define rational temper as the attitudes, exactly as in the case of scientific temper, the attitudes and predispositions resulting from the practice of rational inquiry. Now, one more step. I would like to expand this to academic temper. Academic knowledge is the outcome of research as collective rational inquiry and what is transmitted as knowledge in schools and colleges and other educational institutions. This is academic knowledge. And as I said, it's the outcome of research as collective rational inquiry. And there are some related items, namely academic inquiry. There is a difference between rational inquiry and academic inquiry. Academic inquiry is a special case of rational inquiry. It's a form of collective inquiry needed for the generation and critical evaluation of academic knowledge. This is the part that I want to emphasize. And there is another aspect, another related term, academic intelligence, that refers to the mental capacities resulting from the practice of rational inquiry. So not simply the knowledge, but certain mental capacities, academic intelligence that comes from the practice of academic inquiry. And then I would define academic temper as I define scientific temper and rational temper as the attitudes and predispositions associated with the culture of academic knowledge. And this is extremely important. And I take this as an axiom of education philosophy, at least for me, this is an axiom. While helping the young to understand what is currently taken as the academic knowledge. This is what we normally do in schools and colleges. We transmit academic knowledge and help them understand it. We should also, that is, institutionalized education must introduce learners to the academic culture and nurture academic intelligence and academic temper. I believe that these conditions are not met in current schools and education and schools and colleges. Academic culture, nurturing of academic intelligence, and nurturing of academic temper. In this talk, I'll be concerned only with the last bit. How do we nurture? Do we actually nurture academic temper? And if we don't, how can we do that? That's a central question that I would like to raise. So what are the core strands of academic temper to proceed? One, I would like to discuss 4 of them, actually 5, but I don't think I'll get time for the 5th one, but I'll just briefly mention it. The first strand is a deep awareness of the uncertainty and fallibility of human knowledge, including mathematics and science, and the intellectual humility that stems from that awareness. This was mentioned right at the beginning by people like Bertrand Russell, a certain kind of intellectual humility, modestness, sense of fallibility, and so on. I will give examples for each of these things later in the second part. Right now, let me simply go through a list of the strands of academic temper. The second strand is the predisposition to doubt, question, and think critically about one's own and other people's beliefs and practices. This too was mentioned very briefly in the quotes that I gave earlier. The third, unwillingness to accept conclusions not supported by evidence or proof. I'm using the term proof to mean rational justification. Fourth, commitment to rationality. What that means is rejection of logical contradictions, acceptance of logical consequences of what has been already accepted. So these concepts of logical contradiction and logical consequence are the central pillars of rationality. Abandoning those would be irrationality. Finally, the 5th strand, this is actually very important in education too, dealing with alternatives. Now, there are 2 aspects of dealing with alternatives. One of them is accept positions, views, solutions that are opposed to our own by exploring their desirable consequences. So typically we accept our own beliefs and reject other people's beliefs. This strand is the opposite of that. We consider other people's positions, even if they are against our own. We explore their logical consequences. And if those logical consequences are desirable, those good consequences, then we accept their position and reject ours. That's one. The second part is rejecting our positions, solutions, exploring their undesirable consequences. So we examine our own beliefs, and if the consequences are undesirable, then we reject our own positions. These 2 are extremely difficult, but they can be achieved if we incorporate them in science education and academic education in general. Okay, so I will now proceed, before proceeding to the next part, giving examples for the first 4 strands. Let me ask if there are any questions before we proceed. If there are questions in the chat box, then I'll take them.
So we don't yet have questions. I think it'd be easier if we can take all the questions after this particular portion.
Okay.
Because only now comments have started coming in. So I will collect all of them and I will bring them over.
Yeah. In the meantime, I have prepared this PowerPoint with expectation of questions in the middle. And if there are questions and you would like to raise them, I will be happy.
I will bring those questions forward immediately.
Good. Yeah. So part 2. Let me give you some examples of these different strands of academic temper. The first one is total certainty versus rational justification, a sense of uncertainty, fallibility of knowledge, and so on. And this has to do with two distinct concepts of knowledge. There is a common sense concept of knowledge, which carries total certainty. For example, when we say, I know that the earth is round, I know that P means proposition, some statement. It implies that I'm completely certain that what I believe is true, total certainty. So you cannot say, for example, I know that the earth is round, but I might be wrong. That's impossible. If you use the verb know, the consideration of the possibility that I might be wrong is impossible. The same way, even if you say this about somebody else, John knows that the earth is round, but maybe the earth is not round. Or you cannot say, I believe that the earth is not round. It's not possible. The moment you say no, total certainty sets in. This is the common sense concept of knowledge. And it is also embedded in classical epistemology. Epistemology is a theory of knowledge. The academic concept of knowledge is different. It carries a sense of uncertainty. So in the statement, to the best of my knowledge, this is true, that carries the possibility that I might be wrong. And it is that concept of knowledge that we use in academic knowledge. And academic knowledge can be defined in this way as a body of rationally justified propositions that we believe to be true beyond reasonable doubt, not beyond any doubt. So Descartes, for example, thought of knowledge as certainty beyond any doubt. But that is not the post-20th century idea of academic knowledge. Beyond reasonable doubt, some degree of certainty is needed, but not total certainty. So the question that I would like to raise is, what kind of knowledge does our education system propagate? Is it the common sense concept of total certainty? Or is it knowledge that is imbued with a sense of uncertainty, fallibility, some degree of intellectual humility? The first, the common sense concept, is actually blind faith. We accept whatever our teachers say, whatever our textbooks say, as absolutely true. But that is not what is embedded in academic inquiry. This is not part of academic temper, where we believe that as far as rational knowledge is concerned, these are conclusions, and the conclusions can be wrong. Let me give you some examples of the growing awareness of uncertainty in the history of academic epistemology. Around the middle of 20th century, not the middle of 20th century, the end of 19th century, beginning of 20th century, the paradigm of total certainty of knowledge gave way to uncertain knowledge. Here are some examples. Atomic theory came about, and at that point, atoms were supposed to be indivisible units of matter. This was Dalton's idea, also Democritus's idea. And the idea that atoms are indivisible changed, had to be corrected, as atoms are divisible. That is, atoms are composed of indivisible nuclei and electrons, two things. That also changed. The nucleus, we discovered, was divisible. They consisted of protons and neutrons and so on. And those also became divisible. Now we believe that there are fundamental particles, which are the atomic units of matter. Maybe even that belief might turn out to be wrong 20 years from now. The initial idea of electron was electrons are like raisins on a bun, stuck on the nucleus. And that idea had to be changed as electrons not stuck on the nucleus, but orbiting around the nucleus with empty space. Okay, there is considerable change from Dalton's atomic theory to current atomic theory. And it's very important for us to understand that and the reasons why we rejected the earlier ideas of atomic theory. The same with another example would be theory of motion. In the Greek times, when people like Archimedes worked on motion, the idea was that force is that which causes change of location, or force is that which causes motion. That was changed when Galileo came along to force as that which causes change of velocity. A remarkable difference. So that means Archimedes was wrong in saying that force changes creates motion. Okay, and the switch has extraordinary importance in the history of physics. Let me give you a couple of examples closer to our own beliefs. Is it true that every human being has exactly one heart? We believe that this is true, but can we be totally certain that every human being is exactly one heart? Suppose we take a sample of, let's say, 10,000 random sample of humans, and we check how many hearts a person has. We're likely to find that in 10,000 people, every human being has exactly one heart. But does that justify the beliefs that in the population of humans, this may be true about the sample, but in the population of humans, every human being has exactly one heart? No. The reasoning from sample to population is always uncertain and fallible. Why am I saying this? Because this will be the case if we took a random sample of 10,000 people and checked the position of the heart. It'll be on the left-hand side. But does that justify the belief that it is absolutely certain that every human being has the heart on the left-hand side in the population of humans? No, because we know that 1 out of 16,000 humans have heart on the right-hand side, where the internal organs are reversed, and it is perfectly healthy. There is no problem. So what that means is in every finite sample, even if something is true, no matter how large the sample, how random the sample is, there is always the possibility that in some location that we have not actually checked, this is not true. So even though we have considerable belief that every human being has exactly one heart, that belief is tempered with the possibility that we might be wrong. Somebody in some corner of the universe might exist with 2 hearts or even 3 hearts. Let me take another case. In school textbooks, it is asserted that it is true that acquired characteristics cannot be inherited. And students believe this is absolute true. Well, as it happens, this is simply not true. Okay. If you ask biologists, the practicing researchers in biology, they know that acquired characteristics there are certain acquired characteristics which can be inherited. So the point I'm making is that what we regard as academic knowledge is not absolute truth. It is uncertain and fallible. So it is important that we develop the habit of doubting and questioning what we are told. So my question is, does our education nurture a sense of the uncertainty and fallibility of knowledge as conclusions beyond reasonable doubt? Knowledge is conclusions, and the conclusions can be wrong. And I guess my question is kind of rhetorical because I'm implying no, our education doesn't. What it transmits is dogma, blind faith. Okay, if there are questions, I will take them.
There's a question from Rajgopal. Arvi, you can ask the question directly. Sure.
Yeah, so Mohanan, you spoke about the fallibility and how do we know for sure that say for example the human beings all of them have only one heart. Now the question is there any evidence so far to prove otherwise?
No, there is no counter evidence. So the logic of inductive reasoning says this is true of the sample, and the sample is representative. And unless given absence of counter evidence, it is reasonable to believe that this is true. What that means is I'm willing to abandon my belief if there is counter evidence. So it is the absence of counter evidence that allows us to accept that conclusion, but that means it is tentative. We are willing to abandon it the moment there is counter evidence.
Okay. So in the event a counter evidence emerges, we have to change our belief.
Yeah, absolutely. And that is an important aspect of scientific inquiry.
If I may add to that question, Professor, then it allows for people to come and say that there are people with 2 hearts, 4, 7, 23. In which case, do we say you give me the proof for me to accept that? So, is it that the burden of proof is with the person who proposes a theory, or is there something a greater truth where, irrespective of anybody throwing a question, then it is important for everybody looking for a scientific truth to try to go and find the actual truth? Will it not waste one's time just because somebody comes up with a wild theory?
Yeah, the burden of proof initially, when we propose a theory, before a theory is established, we have found evidence. The burden of proof is on the theory proposer. But once a theory has accumulated sufficient evidence and we believe that it explains a large number of things, then if somebody proposes counter evidence, it is for that person to show the evidence. Burden of proof is on the challenger. So, for example, as of now, the relativity theory is well established. Quantum mechanics is well established. If somebody wants to show that quantum mechanics is wrong or relativity theory is wrong, burden of proof is on that person. So there is a shift. There's a shift between what happens at the beginning of the theory, when the theory is not established, and what happens when the theory is reasonably well established. Then the burden of proof shifts to the other person, the challenger. So that way, science is, in some sense, orthodox, at the same time open-minded and self-correcting. You can't just accept everything that everybody says.
Yeah, that's an interesting point. There are 2 questions related to one of the examples that you gave from Mali Nandakumar and Vaishnavi PK. Both are similar questions. Like, can you give examples of acquired characteristics being inherited? Can we get an example? So I think it has. More than anything, that you gave that as an example. The fact that immediately a question comes is that the belief is that acquired characteristics, cannot be inherited. And now that you are basically saying, that is not true, then it actually shocks the viewer to say, hey, give me an example.
Very good question, good demand. The belief that acquired characteristics cannot be inherited was done on the basis of some somewhat not very good experiments. Somebody cut off the tails of rats, and the rats, had offspring. They cut off the tails of the offspring and so on. Did that several times, but the new offspring always had tails, and so the scientists concluded that acquired characteristics cannot be inherited. But that was just one experiment. There is persuasive evidence to show that there are acquired characteristics that can be inherited. A classic example, we all know this, AIDS. If a mother is infected with AIDS, that can be carried over to the offspring. This is well known. There are also other kinds of things that I will not go into the details. For example, when a pregnant mother is malnutritioned, the baby will be small in size. So this is the kind of acquired characteristics. It is coming from environment and nutrition and so on. But what's interesting is this: when that baby becomes pregnant, it's a girl baby, becomes a woman and becomes pregnant, and even if that person is receives good nutrition before pregnancy, during pregnancy, the baby of that person will also be small in size. Here's a case where the mother has an acquired characteristic, and that is passed on to the offspring. There are lots of similar cases, which I will not go into. It's easy if you type inheritance of acquired characteristics. Everybody knows. Biologists know this. In fact, the experts know this. I have asked the people who are on the committee of the textbook, who in NCERT textbook, where it asserts that acquired characteristics cannot be inherited. And the expert biologist says, I didn't know that the textbook writer was saying that. I haven't seen that textbook. So it is very important to doubt and question textbooks. There's a gap between what the researchers know and what the textbook writers know.
Fair enough. Yeah.
Okay.
Over to you, sir.
Next, the next strand is critical thinking, the next strand of academic temper. Critical thinking I'm going to define as the mental processes that go into the consideration of the merit of something. What do I mean by merit? Sorry, what do I mean by that something? It can be a belief, it can be actions or practices, it can be products, it can be artifacts, and so on. So we want to carefully examine the merit of these things. And by merit, I mean the truth of a proposition, the usefulness of an action or product, ethical rightness or wrongness of an action, the value of something, the beauty of something. All these are different types of merit. And critical thinking is the evaluation of the merit of something. All right. Let me give you some, this is a kind of abstract definition. Let me give you some examples of actual critical thinking that can be practiced in the context of academic knowledge that we receive from schools and colleges, textbooks, teachers. Okay. I'm going to assume that you know the basics of, the students here know the basics of classical mechanics, laws of motion, and so on. So, and let me say that I have asked this question in many classes. For example, in physics honors class, I have asked this question. Okay, two balls of equal size. One is made of lead, and the other is made of styrofoam. Styrofoam is, I don't know what you call it, cork-like thing, packing material. They are dropped from the same height at the same time. Will they both touch the ground at the same time, or will one of them reach the ground before the other? And all students, honor students, and even master students say, no, the lead ball will come down faster. And you pretend surprised and say, but didn't Galileo say that the weight doesn't matter? Things fall at the same rate, whether it is lead or feather. And the students give you a, all-knowing smile and say, oh, this is because of air resistance in the atmosphere. Okay, sure. And then you ask, what is air resistance? And isn't air resistance a function of the area, surface area? And they say, yes, air resistance is a function of the surface area. Then you say, but I said that the two balls have exactly the same size, so their surface area is the same. How come the lead ball comes down faster? Once you point out that there is a problem in the concept of air resistance and Galileo's statement, of course, I asked this question in such a way that they would be stuck. There is no answer. Students sit there and wonder they are in trouble. At this point, they should realize there is some problem in their knowledge of classical mechanics. I'm not going to give you the solution because I would like to make you feel uncomfortable about not knowing something. Okay, so I'm going to go on to the next part. This is for you to think critically, especially the students who are listening to this. And this is something that lots and lots of people have difficulty with, the specialists in physics, the undergraduate students in physics, master students in physics. Imagine a ball moving at constant velocity, and that ball hits a stationary ball. Okay, there's a ball moving at constant velocity. This ball hits a stationary ball. Now we know the equation F is equal to ma. Now this is constant velocity, so that means the acceleration is 0. And given that acceleration is 0, it follows that force is 0. So that means that the force that the moving ball exerts on the stationary ball is 0. So there is no external force on the stationary ball. The stationary ball should remain stationary. But we know that is not the case. Okay. So what's wrong with this reasoning? Definitely something wrong here, but what exactly is wrong? All right, I leave that to you. You should start thinking about Newton's laws of motion and so on. I'm not suggesting that Newton's laws are false, but I'm suggesting that there is a lack of understanding of classical mechanics. And that will be revealed only by subjecting it to critical thinking. Another example. Newton's first law of motion says that the velocity of every object in the universe will be constant unless an external force acts on it. Is that true? Consider, for example, a bird sitting on the branch of a tree, and that bird might start flying without any external force acting on it. Is the law wrong? Okay. You cannot say that the bird has internal energy or whatever, because Newton's law says unless there is an external force acting on it, unless there is an external force acting on the bird will not move, will not change from zero velocity to positive velocity. So what do we do given this logical contradiction between what Newton's law predicts and the behavior of the bird? Thinking about that is critical thinking. Notice that I'm suggesting critical thinking, thinking critically about the textbook knowledge. My last example of critical thinking, we are told in school textbooks the following things. One, similar charges repel each other and opposite charges attract each other. We are also told that lightning is caused by positively charged clouds or negatively charged clouds. And these are negatively charged clouds and so on, are configurations of water molecules. So you have positively charged water molecules and negatively charged water molecules in some cloud. But if the law is right, how can you have positively charged water molecules in a cloud? Won't they repel each other? And wouldn't they move away and then form negatively charged? How come molecules with the same charge? Yeah, why is it that positively charged molecules come together as a cloud and negatively charged molecules come together as a cloud? Shouldn't they go away from each other and positive charges and negative charges come together to neutralize the charges? So charged clouds should not exist according to this law. If that doesn't make you uncomfortable, okay, that should be surprising. And scientific inquiry begins with that kind of discomfort arising from critical thinking. Okay, my question to you, does our education nurture the habits of doubting, questioning, and critical thinking? Does our education system allow you to question your teachers, to question your textbooks, and to question the so-called experts? If it doesn't, there is something wrong with the education system. The education system does not nurture scientific temper, let alone academic temper. All right. Some quick questions.
There is a pretty long question which I probably take to later because
Okay.
it covers your fifth point actually. So I have a question. I mean, all the questions that you just now raised, the 4 questions that you raised, I'm pretty sure I can answer them myself to my satisfaction and possibly to your satisfaction, right?
Uh-huh.
The idea that you are trying to bring here is that such questions at any point in time can be raised about any of our understanding, and there is an answer, or there is a there is a good explanation, right? And the question I suppose what you are trying to bring out is that, have you asked this question yourself?
Exactly.
Or if somebody else is raising this question, are you in a position to try to address these questions? Or are you equipped sufficiently in your education system to take them up and try to answer? Even if you make a mistake, that is okay. But are you asking these questions, or are you trying to attempt to answer such questions?
Yeah.
Can I take that? Because fundamentally, these are not really trick questions. If you understand the fundamentals, it's fairly clear. Well, let's take, for example, the one ball transferring the force onto the other. At the point of impact.
No, don't say that.
Okay, I won't.
Keep it.
So, I understand that each one can be answered, of course, to different levels of understanding that people do have. But I take your point that, if I go to a school, get a bunch of students, throw these questions, not with the intention of sucking the hell out of them, but that, is the process itself training them to take on questions like this and not be totally, psyched out by a question and turn off and run away.
Yeah. And the deeper point that I'm making is that every textbook and every examination question should raise such questions so that students are in the habit of doing this, not simply taking it down. And in some cases, when they raise such questions, it may turn out that the existing body of knowledge is actually wrong. In a subject like physics, that is not so easy, but there are other areas of knowledge where when students raise questions that can lead to research and it can result in change of academic knowledge. So it is important that students have that habit. Okay, in the examples that I have raised, I know how to solve those problems, but most students don't. And I did not learn it from my education, I should say. I did not learn that from my school education or college education.
True.
I learned it from outside, in spite of the system, not because of the system.
Fair enough.
Okay.
Fair enough. Yeah.
So the next strand has to do with proof. Now, giving proofs, when you make a claim, a knowledge claim is something that we believe to be true and something that we want the other members of the community to accept as true. That's a knowledge claim, something that you claim to be true. In mathematics, there is a tradition of providing proofs to conjectures. A conjecture is something that we believe to be true, but to be accepted as true, we must give proof. And giving proofs is part of math education. But that is not part of science education. In science education, we assert what we regard as true, but we do not provide any proofs, we do not give any evidence for it. So let me extend the notion of mathematical proof to the ability to construct proofs. Okay, I'm not talking about proofs that the teacher has given or the proofs that the textbook has given, or maybe changing that proof slightly to create a different proof, but something surprising. Okay, let me take this question. Suppose the Euclidean geometry assumes that two straight lines will not intersect in two different points. Okay, Euclidean geometry also assumes that a straight line, when extended, will not meet itself. Suppose you change that axiom. Okay, can you get this result? Any two straight lines, when extended, will intersect at two distinct points. Let me read that again. Any two straight lines, when extended, will intersect at two distinct points. Can you prove that by changing the axioms of Euclidean geometry? Okay, mathematicians will be able to do this, but I'm asking students, does this strike you as even possible? Let me simply say, yes, I can prove it, but I'm not going to tell you what the proof is. But if the proof is not in Euclidean geometry. Another question, can you prove by changing the axioms of Euclidean geometry? In fact, the same axiom can be changed to get this result. The sum of angles in a triangle is more than two right angles. And it can be up to three right angles. This might strike you as preposterous if you are used only to Euclidean geometry, but I'm suggesting that you change the axioms of Euclidean geometry, and then you can prove it. So that's what I mean by the ability to construct proofs given certain axioms and definitions. Truth in mathematics depends upon what you state as your axiom and your definition. It is that ability that is important as an important strand of academic temper. So let me take something outside of mathematics. The ancients believed that air and water are elements, but modern science tells us that air is not an element. What is the evidence to show that air is not an element, that it is composed of elements? The standard proof given is the candle experiment. You light a candle and put that in some amount of water, and you put a vessel on top, put a beaker on top of that, and you find the candle flame disappears and the water level goes up. And the explanation given is the following. that there is oxygen in the air, and when the candle flame uses up that oxygen, and oxygen is 1/5 of air, and when that oxygen is used up, the water level goes up because the pressure goes down. This is a standard textbook explanation for air having oxygen, or rather argument for air having oxygen. But consider this. What happens in the combustion? The candle flame takes oxygen from the air, takes carbon from the candle itself, the wax, creates carbon dioxide, and puts it back in the atmosphere. So there is, instead of just being oxygen, now you have oxygen and carbon dioxide. So the pressure should be greater, not less. So the experiment that is shown in textbooks actually shows the opposite. So what is the explanation for the water level going up? And whatever it is, whatever the explanation, does it show the evidence for oxygen? If you have scientific temper, you should be doubting your teacher, doubting your textbook, and say, what you're saying doesn't really convince me. It in fact convinces me the opposite. Second example, we are told that the Earth is not the stationary center of the universe. The ancients believed that the Earth is stationary and that the Earth is the center of the universe. Modern science, modern astronomy tells us that these statements are not true. The Earth revolves around the sun and so on. Why should I believe that? My experience tells me that the Earth is stationary. It doesn't move. Why should I believe, contrary to my experience, that the Earth moves? That question is not easy to answer. So when I teach undergraduate students, it usually takes me about 10 hours to go through the argument. This is not something that you can answer in 5 minutes, because what you have to do is to develop the heliocentric theory. Heliocentric means sun-centered solar system, versus the geocentric theory, which is earth-centered theory. Both theories can explain the observations up to a certain point extremely well. They're equally good. And you have to develop both these theories side by side and show that at the end, there exist certain facts that the geocentric theory cannot explain, or can explain much better. And that demonstration, that proof, as I said, takes about at least 10 hours in a classroom, in an undergraduate classroom. And I have not seen a single textbook going through that argument. And I'm pretty sure that most students do not know that argument. Why we should believe. I'm not saying that the heliocentric theory is wrong. I'm saying students do not know the evidence, the arguments for the heliocentric theory. Another case in point. We are told that, let me just take a specific case of the evolutionary theory. All species of animals on the earth evolved from a single ancestor species. So there was an ancestor to all animals, and all of us are descendants of that ancestor. Okay, actual experience is, if you have two dog parents cannot give you a cat. Two cat parents cannot give you a dog. So this is called like begets like. That means to say the species of the parents and the species of the offspring are the same. Now, no matter how many events of reproduction has happened in the chain of reproduction that we call evolution, there is no single chain where the change of species can occur, according to this. So why should I believe that we evolved from a single ancestor species? Humans, chimpanzees, orangutans, dogs, cats, elephants, mice. That question, I have looked at many undergraduate textbooks in biology, and in fact, textbooks in evolutionary theory. I have not seen a proof that convinces me. I'm not saying I believe that the statement is false, mind you. If I were asked that question, I can give you a reasonably good proof, but I have not seen a good proof in a textbook. And it is the responsibility of textbooks and specialists to give rigorous proofs for claims of this kind. Otherwise, what they're asking students to do is to accept statements on blind faith, which is the opposite of scientific inquiry, scientific temper, opposite of academic temper. We must not accept things without adequate proof. So my question again, does our education nurture the habits of asking for proof or evidence and arguments for assertions and claims? Or does it nurture the habit of accepting what the teacher says, what the textbook says, what authorities say on blind faith? What kind of education do we have? I know these are somewhat uncomfortable questions, but so I will wait. If there are questions about this, I'll answer them.
Yes, there is a question from Ramaswamy. It says the speaker seems to be hinting that the beast called critical thinking is a transferable skill and has to be part of education. Is it possible? D. Willingham, I think that's the name, has some very critical ideas about this notion.
Yeah. Yes, I believe that critical thinking is a transferable, not a transferable skill, but a transferable ability and a transferable habit of mind. And what that means is that once you know how to construct proofs in mathematics, you can use that to construct proofs in ethics. But of course, it requires a certain kind of education. I have designed learning materials and courses and so on in such a way that students can do that, can transfer their thinking abilities from one domain to another. But that requires a certain, what I call transdisciplinary ability to move from mathematics to a higher realm, and then from there to the other domains, or to move from physics to an abstract realm, and from physics to transfer it to biology or to ethics and so on. I know that what I have said is only a kind of very crude response, but to explain what I mean by that, transferable abilities and habits that are transferred through transdisciplinary thinking, that will take me a separate 1 hour session, or maybe 2 hour session, I'm not sure. So I will simply say, yes, I believe that critical thinking abilities, or all these strands of academic temper that I have mentioned, are all transferable. And the other part, the second part of the question was, sorry, I forgot. What was the second part?
I think from his spelling, it seems to indicate somebody called D. Willingham has some very critical ideas about this notion. I'm assuming I'm pronouncing that name correct. It's unfamiliar to me. The very topic itself is unfamiliar, so maybe you have come across
Sorry,
the
about
name.
the transferability.
Yeah.
Yes, I have seen the research literature arguing in educational circles that skills are not transferable. The way it is done currently, without any transdisciplinary framework, yes, of course, they are not transferable. So I can give examples of what that is. For example, the idea of double-blind experiments is not transferable to the idea of to the domain of infectious diseases, and they have a separate methodological strategy for that. And people take these things as fragments. However, once you realize that the double-blind experiments, the abstraction of double-blind experiments is causal reasoning, and if you learn how to engage in causal reasoning, then you see that the formula for, or the methodological strategy for infectious diseases is simply the same thing, causal reasoning. So you need to pop up to a slightly higher level of abstraction. So the reason why many educationists believe that skills are not transferable is because education does not nurture transdisciplinary concepts. Of course, without the transdisciplinarity to support it, they're not transferable. But in my own experience, my students have no problems in transferring, for example, from linguistics to history, or from mathematics to ethics and so on. They are transferable. If you learn how to do this in one discipline the right way, not in a fragmented way, not the way it is done currently, then they are transferable. So the the claim of these educationists should be, given the way things are taught in educational institutions, nothing is transferable. Yes, true. But that is the fault of the education system.
I have a couple of questions related to the points that you brought up. Take for example, you talked about the that it takes quite a bit of your time to explain or to prove or to convince your students about the heliocentric theory, where geocentric theory is an obvious thing. You just look around and the sun seems to go around, the moon seems to go around, and you are at the center of the universe, right? But all these, let us take things that are microscopic or things that are too huge. I mean, how can I go and prove to somebody that this is how the structure of the atom is, and there are orbits and electrons are sitting all over the place according to some complex quantum mechanical equation, where it will take me years and years and years to even answer the questions that a student raises. So the easiest for me is that this is what Dalton said, this is what J.J. Thomson said, this is what Rutherford said, this is what Niels Bohr said in terms of a certain model, and the model had flaws. And then came a whole bunch of scientists, and they all are sort of students of Niels Bohr, if you may say, who then drastically changed the whole model and then presented something. But in reality, even that model had flaws. So we constantly keep trying to fix it. If I say this to my student, the student will say that, what you are saying is that everything is a flawed model. The so-called standard model that you are talking about today is flawed. The string theory that you sort of try to indicate now also seems to be flawed. I mean, you can't, at that point, how will a 11th standard teacher even be able to present the modern knowledge in a succinct form, other than a bunch of bullet points in a PowerPoint like this? Say, hey, this is what it is. Go and do higher studies. Figure out yourself. Let me get on with my work. You get on with your work.
Yeah. Okay. Here is what I would say. In school education, let's say class 1 to class 10, there is a whole bunch of stuff that students don't need after their education. Many of the things that they learn in the curriculum for class 1 to class 10, they don't require for anything in their life after their degree. Number one. So those things can be removed. From some of the things that they need in their later life, if they have the ability to learn on their own, they should be able to learn after their school education. So for example, if I took biology as my subject, and then let's say when I'm 30 years old, I suddenly had the desire to learn Indonesian history. As an educated person, I should have the ability to learn Indonesian history by reading books on history. My teacher doesn't have to teach me, my textbook doesn't have to teach me. That can be reserved for independent learning. So that also can be cut out, anything that you can learn on your own. So what education should focus on is the ability to think critically by taking a few examples. So heliocentric theory is a very good example. If you spend 10 hours on heliocentric theory, there might be things that you may not be able to do in your school. For example, take the formula E is equal to mc squared. That is not something that you expect students to 10th grade students and 9th grade students to understand, or let alone ask for evidence. So what I would say is that as far as possible, do not present to students things that they cannot question and critically evaluate. So don't tell, for example, don't tell 5th grade students that the earth revolves around the sun, because 5th grade students do not have the mental maturity to go through the argument. So present the stuff when they're ready to engage with the reasons. That's one principle. And then they should also know that they cannot understand the evidence for everything that they're going to have. So they should have the ability to say, I don't know the reasons, but this is what the scientists say. So since I don't have the time or the eternal time to engage with the reasoning, for now, I will say the scientists have, they have a good track record. So for now, I will accept it tentatively. It may be the case at a later point in my life, I've discovered that this belief is wrong. So there's a different kind of attitude that you're nurturing. I'm not suggesting that everything that students learn must have evidence, argumentation accompanying it. Some things they will be able to, some things they will not be able to, but they should be able to tell the difference of things that they accept on the basis of their own critical thinking and things they accept because of their trust in trustable authorities. But even those things must be accepted only with that sense of uncertainty, the sense, yes, I don't have the capacity right now to engage with it critically, but I will take it as true until if I have a chance to think critically, I will do that. That's a very different attitude. My advice to the teachers is, do not pretend that this is absolute truth. If the student asks a question, why should I believe it? And the teacher doesn't know the answer, the teacher should say, yes, that's a good question. You should pursue that question. I don't know the answer because I, like you, was brought up in the same kind of education system. So the teacher should be able to say, I don't know. That's where education begins. That's a completely different paradigm of education.
Wonderful. Thank you. There are a couple of appreciation message from Vaishnavi and Matangi Venkatramani. So yeah, okay. I think your explanation has made a lot of sense. But okay. There is, though I don't want to stretch it further, the fear that a teacher has of standing in front of the student and saying, I don't know, is by itself a topic that is worth expanding upon at some point. When that happens, then they are absolutely sure of themselves, of what they know and what they don't know and what they are not so certain of. So they know and not know. If they can be honest and also convincing the students that it is always going to be that way, even to the ultimate topmost scientist in the world or the exponent in a particular field, it is always going to be this way, that there are certain things they don't know. It will be nice. Thank you.
Absolutely.
Thank you.
The teacher should be able to say, I don't know. And the teacher should also be able to engage in argumentation with the student. And if the student convinces the teacher should say, I was wrong and you were right. Those two sentences are extremely important in education. Those two sentences nurture academic temper. Okay. I've been talking about rational temper and so on. So let me outline two central pillars of rationality. One of them is logical consequence. And logical consequences of a set of statements are the statements that we can infer from a given set. What I mean by that is something like this. If you are told that Zeno is in Greece, then Apollo is in Italy. You don't know who Zeno is, you don't know who Apollo is, doesn't matter. You may not even know where Greece is, where Italy is, and so on. Nothing matters. You are told that if Zeno is in Greece, then Apollo is in Italy. You're also told that Zeno is in Greece. Given these two statements, you don't know the truth of those two premises, but if they are true, the third statement is true. Apollo is in Italy. So Apollo is a logical consequence. The third statement is a logical consequence of the first two statements. This is one of the pillars of rationality. And it is irrational to accept the first two statements and reject three. So violating this commitment that if you take certain premises as true, you should also take their logical consequences as true, is one of the pillars of rationality. Violating it is irrational. One. Second is that of logical contradiction. The statements that Apollo is in Italy and Apollo is not in Italy are logically contradictory. Logical contradiction is the combination of two statements, one of which negates the other statement. And it would be irrational to accept both 1 and 2 at the same time as true. One of them must be rejected. This is the second pillar of rationality. Violating either of those would be irrational. And education must develop a certain value attached to rationality and a commitment to these two principles of rationality. Let me go through some examples. So take the familiar distinction between solid and liquid. These are examples that I have used again and again, like the heliocentric theory. But many of you have heard me using these examples, and I cannot find better examples. These are telling examples for people who haven't heard about them. So if you have heard me talking about these things, please don't fall asleep. I will continue using these examples till I die because those are great examples. Okay. This is what textbooks tell you. A solid substance has its own shape and volume, but a liquid substance has its own volume but not shape. It takes the shape of the container. Okay, I think the people learn this in primary school. Now let me ask, which of these, are these things solid or liquid? Table salt. If you take, say, table salt and put it in a container, it takes the shape of the container. So according to the definition, anything that takes the shape of a container is liquids. Therefore, table salt is liquid. Cloth. If you take a piece of cloth, put it in some one container, it takes the shape of that container. Another container, it takes that shape. Cloth doesn't have its own shape. So cloth must be liquid. Soap bubble, on the other hand, is spherical. So soap bubble must be solid, according to the definition. If you are committed to rationality, you should say, I cannot accept the definition of solid and liquid and my judgment that table salt is solid, table salt is solid, cloth is solid, wood is solid, and soap bubble is liquid. There is a conflict between, there is a mismatch or logical contradiction between the inference, the logical consequence of the definition, and our own belief. Either you change your belief that table salt is solid, or you reject your definition and look for a better definition. That's what commitment to rationality means. Another example. Again, this is taken from textbooks. I'm not sure whether it is 8th grade or 9th grade, some textbook. In fact, one of the teachers in a school brought this to me because a student raised this question. The chapter on microorganisms says, microorganisms are invisible to the naked eye. Fungi are microorganisms. Mushrooms are fungi. 3 different sentences in the same textbook, the same chapter. What's the logical consequence? It means that mushrooms are invisible to the naked eye. But we know that is not true. We can see mushrooms. So either we can reject one of these 3 statements or believe that mushrooms are invisible. That is obviously not true as far as our experience is concerned. There is something wrong somewhere. A rational mind should question the combination of these 3 statements. Okay, this can be fixed by changing certain things, but I'm not going to do that here because my enterprise to create discomfort so that you will engage in these questions on your own. But the moment I give you the solution to these problems, learning stops. Let me give you another case that I find, I take a sadistic pleasure in asking these questions, I should confess. So you have all learned that straight angle is an angle of 180 degrees. Right angle is 90 degrees, straight angle is 180 degrees. So if you have a line AB and you put a dot, a point in the middle C, angle ACB is a straight angle. All right? Now take a triangle ABC in which angle ABC is a right angle. Pick any point D on AC. We know that any straight line has infinitely many points. So take one of those points D on AC. Now, from the definition of straight angle, it follows that ADC is a straight angle and it has 180 degrees. What that means is that in every straight line, you have infinitely many straight angles, infinitely many 180 degree angles. Okay? So what is the sum of angles in a triangle ABC? Okay, in a right angle triangle, this would mean there is one right angle and then there is infinitely many 180 degrees angle. Definitely, it cannot be the case that the sum of angles is 180 degrees. How do you eliminate this logical contradiction? It can be eliminated by appropriate definitions, but again, I'm not going to do that. I will leave this to you for you to struggle with. But the point I'm making is that thinking about such things is an important part of the rational mind. Rationality allows us to cross-check things, to develop a certain kind of intellectual hygiene, a quality control mechanism. Rationality cannot tell you how to discover things, but rationality can tell you what is wrong. Okay. And my question to you is, does our education nurture a mindset of rationality and a commitment to it? Obviously, my answer is no, it doesn't. All right. Again, short questions and answers. Or shall we just proceed to the next part? Is going to be fairly quick.
Badri, you're on mute.
No, there are no specific questions. Please go ahead and we'll maybe bring in some questions to it.
All right. So the part 3 is reforming curricula. This is very brief. I have the following proposals about bringing in academic temper in school education and college education. There are certain things that we can do, but we are not doing them right now. One of them, discuss issues of proof, evidence, and arguments in every subject, not just mathematics, in physics, in astronomy, in biology, in sociology, in psychology. Psychology, I think they do present some experimental evidence, but it should be there in every subject, so that students get used to the idea of asking for evidence or proof. Devote at least 2 hours a week to rational inquiry from class 6 to class 10. Rational inquiry, like mathematics, should be a subject in the school curriculum so that students learn how to engage in rational inquiry across subjects. It's only 2 hours a week. It's not a great deal. And as part of B, the subject of rational inquiry, introduce students to different modes of reasoning and logic. That is, by different modes of reasoning and logic, what I mean to say is not simply deductive reasoning used in mathematics, but also inductive reasoning, and this term may be unfamiliar, and also abductive reasoning. I may not have the time to elucidate that concept. There are multiple forms of reasoning and logics that come under these 3 categories. There are different kinds of inductive reasoning, different kinds of abductive reasoning. It's important that students be taught these different forms of reasoning and logic so that they can use them in different domains. If these three conditions are met, if they're done well, I think we have a chance of helping students acquire the rational temper, the different strands of rational temper. Thank you for listening. And now, final questions and answers.
Okay. I have a question. Are we at 2 levels? Are we putting too much of demand on the very education system itself by trying to demand this level of rigor? And what would be the impact on, I mean, is it that it may make sense only to a very, very small percentage of the students themselves, right? It's like, for example, I'll give you what happened in Tamil Nadu, right? This NEET came as a big issue the moment it was introduced, because Tamil Nadu did not have any entrance exam for medical, engineering, everything was abolished. But when NEET was imposed, something had to be done. And the way the education system acted here was by making the syllabus extremely heavy and complicated.
Yeah.
Not just for science and math, for biology, accounting. Okay, biology I understand because it is meant for NEET. But commerce, accountancy, psychology, in all kinds of subjects which had nothing to do with the NEET itself, right? So, are we in this, in this desire to introduce critical thinking? Would we go the other extreme and try to completely change the education system, which will make it extremely difficult for both the students and the teachers? Are they even capable? Are they even interested? Is it even needed? I'm asking a very, I don't know whether it is the right question, but I just wanted to ask this.
Okay. Let me take one of these questions that you asked. are our students capable of critical thinking and rational inquiry? My answer is, unless you have a serious brain impairment, yes, most human beings, I would say something like the majority of human beings are capable of it. This is like saying the majority of human beings are capable of learning how to draw basics. So I can teach perspective drawing to almost everybody. However, can they draw like Rembrandt? No. Can they inquire like Einstein? No. Only a small number of people can do that. So there is a huge range of basic rudimentary inquiry abilities and critical thinking abilities, which everybody can acquire. And this is all that I'm asking for in school education. Not thinking like Einstein, not thinking like Bertrand Russell. And I think that is indeed possible. So what that means is that the goals of education should shift, should not be restricted to communicating a body of knowledge and helping students to understand it. It should also focus on certain abilities that go with that body of knowledge. And my proposal was just 2 hours a week from grade 6 to grade 10. Not a huge amount. Of course, that would mean that certain other parts of the curriculum should be cut. And a great deal of the stuff that students learn anyway are unnecessary. In fact, I don't remember anything useful in my school education and college education subsequently. Anything that I find valuable today, I learned on my own, not from the education system, but on my own, from the library, from conversation with various people and so on. So the weight of the body of knowledge that the education system expects students to have should be minimal. That's important. Not increase the burden. The other part is it cannot be done in one step as a revolution. It has to be done incremental steps, which is why I said just 2 hours a week. That is not a great deal of curricular time. And if we introduce that, if students learn inquiry and critical thinking from these 2 hours and from their own textbooks and so on, teachers would also learn along with students. So we need teachers who can engage with it. And during that transition time, it will be a little bit of anxiety for both teachers and students. But that is bound to happen when something new is introduced. So introduce it slowly, carefully. But we should have a different view of an education system 30 years from now, not immediately. What happens in educational reform is that somebody makes a decision and then they say, okay, this must be implemented tomorrow. Every decision that I have seen has happened like that. Before people have had a sense of what that implies. And they mess up stuff. And we should not do that. So your worries about such unreasonable decisions, not the goal. The goal has to be implemented very, very slowly.
Kopu, you had a question.
I unmuted myself. Yeah, I think one of the questioners asked this question whether, and I'll just rephrase it a little bit. Is it teachable kind of thing? I mean, the spirit of the talk I see what you're trying to do. People are not thinking critically, but I don't know when any person gets the motivation or the light bulb goes off saying, oh, I didn't think of this at all. And I'm not sure it's that straightforward. Let me give a metaphor. Scientific temper, I think we had Jawaharlal Nehru talk about we must inculcate a scientific temper. We have not done that. Okay, no country has done that. A small percentage of the population of a country has some sense of scientific temper. In most things, I think you can see obviously that we have not developed. But is there such a thing as scientific temper at all? Is my question. It's like I use a metaphor. Can you inculcate a vegetarian temper in a tiger or a lion? I mean, or not vegetarian, herbivorous.
Yeah.
Vegetarian is a little loaded. Can you teach a lion to eat grass or something like that? Or what if the other fields that we don't think about? A musician may say you must all have a musical temper. A farmer must say we are 65-70% of the population. The country doesn't know most of the country, most school educated people can't tell the difference between millet and wheat. they've not seen it raw, right? So we must develop an agricultural temper. Or a geography teacher must say we'll develop a geographical temper. Every person will bring in their perspective on that. And where do you go there?
Okay, there are a couple of things that you raised. One is it teachable? My own experience tells me, yes, it is. Unless you assume that human beings are genetically stupid. If they're genetically stupid, of course, you cannot teach, for example, chimpanzees to develop mathematical abilities. Maybe some basic rudimentary number stuff. So let me take the example of cooking. Not everybody can be a chef, but basic rudimentary cooking abilities you can develop, if children watch their grandmothers in the kitchen and have some interaction with the grandmothers and so on. So all these are like drawing, like cooking, like dancing. People can develop some rudimentary abilities, not high abilities, but rudimentary abilities. And some of them will become researchers. If you learn scientific inquiry and critical thinking in school, then you will be a researcher. Otherwise, your chances of becoming a good researcher will be bleak, which is why there is very little research in India. The other aspect is, what do you mean by agricultural temper? Agricultural temper is some rudimentary ability to garden, to farm, and so on. Again, that can be done with minimal effort. It is not a great deal. So it is not the kind of agricultural temper or chef temper or, various kinds of tempers with perfection in mind, high end in mind, but, basic stuff. So there is no problem in developing that every educated person should learn to cook a meal, rudimentary stuff, to be able to draw a face if you feel like, to be able to sing even with some flaws. Can you improve it is a question. Is it the responsibility of education system to take a learner from 0 level to, let's say, 0.5 or 0.1? I'm not saying 100%. So we have to rethink the nature of education. What is it that educational systems are trying to do? Is it simply to transmit a body of information and the best case, a body of understanding? Or is it certain mental abilities? Can education make people more intelligent? My answer is yes.
You just said it yourself that it doesn't. You learned things on your own. The education system didn't teach you anything.
Yes, I learned.
And we all feel that we're not. We all feel that at some point, right? We feel big gaps in what formal education has given us. And I said, I wish I'd learned this better at this particular age, or I wish I'd understood. This concept that I should have learned when I was 12, I only understood when I was 35 or whatever your age is. Something. We all feel that at some particular stage. I'm not sure there's any universal answer to that.
No, let me put it this way. I learned most of the things that are valuable outside of the school and education system in India. Yeah. But my education at MIT was a drastic transformation where I learned something truly valuable. And I have spent the rest of my life learning more. So what I acquired on the basis of my 50 years of work, I think I can now construct a system in which my students can learn in 5 years. That's worth it. So if the people who learn in spite of the system is, let's say, 0.1%, if education brings it in, that effect can be accomplished for 20%.
Let me completely come at this from an orthogonal view, because a lot of things we don't learn is because our teachers don't teach us well. Our teachers present information without exciting or making it interesting. Sometimes you have good teachers, but they are dull teachers. I mean, they make it boring for most people, but they get through to the small percentage who's interested. And that's not necessarily the teacher's fault. It may simply be the student situation, the person's interest and so on. And and we have that particular situation across the thing. But today we have a lot of things I'm learning, like what you did. A lot of things you're learning, we are not any longer confined to the one teacher in school or one tuition teacher that we are forced to. But if you have like 100 million teachers on the internet, the difficulty becomes finding the right person. And sometimes somebody out there, and that person becomes popular, teach us something far better than your university teacher.
Sorry, let me interrupt. You're talking about pedagogical strategies.
Yeah.
I'm not talking about pedagogical strategies, but education.
I'm not talking about strategies. I'm saying not about strategy. I'm talking about learning. It may simply be that you're not able to understand a particular concept, or you're talking about a bigger concept.
I'm not talking about that aspect at all. Not the aspect of understanding, but shifting the education goals in such a way that certain mental abilities are inculcated, not simply understanding. It is not sufficient to understand classical mechanics. It is important to go beyond that to acquire certain abilities of inquiry and critical thinking. That's a very different issue. I'm not denying the importance of pedagogy, but that is not sufficient. You have to shift your educational goals. And is that possible? Yes. And all you have to do is I would invite you to take a look at our inquiry course offered by Think, or the materials. Actually, all you have to do is to go to our learning materials at our website. And there is so much of learning materials that all students can learn from. Even though it is not in an organized way, we have lots and lots of cases. So, for example, there is a course on constructing theory using geometry, not something that is part of school curriculum. So if you produce those learning materials, students will learn on their own from those materials. You don't need teachers' mediation. It is possible. And I'm saying that it is possible because of the work that we have been doing for the last 45 years. We have practical experience of doing this. We have experience of teaching linguistic students so that by the end of the second year undergraduate program, they become extremely good researchers. And that experience has led us to do the same thing in other subjects. It is possible. But the only way to convince you will be to ask you to go look at those materials. And if you have children, try out these materials on your children. Then you will see the difference.
Okay.
Professor Mohanan, there is a question from, I think, a teacher, Shanti, says critical thinking, can it be developed or is it a natural thing? From my experience as a teacher, critical thinking and questioning comes naturally to some students, but I try to make students think critically, they get confused, meaning other students. So it is natural for some, but not so for a larger bulk of student community.
Yeah. This is what the teacher Shanti says, is that some students have a natural talent for it. This is like saying some students have a natural talent for drawing, for painting, for dance, and so on. Now, I don't have a natural talent for music, but I have been able to work on it to get some level of competence in music. I have a natural talent for drawing, so I can do much better than others. So as I said, don't aim too high, but some rudimentary capabilities of critical thinking, regardless of talents and gifts and so on, everybody can acquire, and the teacher's responsibility is to do that. And why are the students confused? I don't know. I have to find out what you did in class so that students got confused and what you mean by confusion. Sometimes some confusion is good for further learning. So I'm pretty sure that the examples that I gave led to some amount of confusion on the part of students. But that is productive confusion. Confusion that says, I have not understood what I thought I understood. That's a good thing. Recognition of one's own ignorance, calling that, if you call that confusion, that's a good confusion. Because unless you recognize your own ignorance, you will not move towards knowledge.
There's a question which I also had. Vaishnavi is, what we feel positively about critical thinking can be viewed as a burden by many. Using these brains for reasoning is a little exhausting. That's why many feel it bothersome. Let me just expand. I mean, this is Vaishnavi's point. So this is one of the things. I mean, it is nice if let us say that you are giving me interesting math problems. I'm going into sort of teaching learning, and it is really intriguing. And for some students, they can just go hack it, actually make it work, and they're exhilarated. They want more and more and more. That is one branch. But a whole bunch of others, it is so tiring for them that they are also trying to do what you are asking them to do. Critically think about this, ask questions, but the mental capacity, there are limitations. I'm not just talking about mental capacity, maybe their environment, the kind of household they are coming from, the support system they have access to, or even encouragement when you are asking the child to do other things, go and fetch water, to the boys versus girls, and entrenched notions of all the things that are happening in our society. Sometimes it may be, not sometimes, many times it may be like too much of a pressure on them that they may not even want to be part of that. I mean, I'm just wondering aloud.
Yes, the point you're making is that, okay, let me compare physical fitness with intellectual fitness. If we agree that physical fitness is important for human beings, and if we, then we should also, by this analogy, we should say intellectual fitness, higher mental capacities are also important. It is desirable, at least. Now, it may be the case that certain people will take the idea of physical fitness to an extreme. They will run and they will do lift things and so on. Me, I don't think I will, as a child, I hardly ever cared about physical fitness. But if I had a different system in which I was attracted towards that, I didn't have that opportunity, so I never entered that line at all. Now, what the system should do is to attract students to develop these different kinds of fitnesses rather than enforce it on them. So if a student doesn't like mathematics, we should ask, why is it that the student doesn't like mathematics? And then make it attractive to students so that they will get addicted to mathematics. This is what we do. We don't force anything on students. We make it attractive so that they will pursue things on their own. As for time and so on, yes, different students have different, or teachers, learners have different requirements of time. But if you can find something like 2 hours a week, that's not a great deal. Okay, and the kind of abilities that you can acquire by investing 2 hours a week, all you have to do is to maybe sacrifice the time that you spent on your smartphone. Or time that you spend in restaurants or doing a whole bunch of other things. So dedicate at least 2 hours a week or 3 hours a week on developing your intellectual fitness. That's all that is necessary.
I don't think time itself is a problem, Professor. If we, even if we don't have solid proof that this is good, I think it is worthwhile. Like, the very point that you talk about, as in, I don't know exactly the value of physical exercise, but we take it as good. I mean, yoga, we take it as good, and we just do that because it can't hurt you. At least, we are coming from that direction. So this can't hurt you, right? The challenge is in terms of, encapsulating this in our, we look at it as, WHO says critical thinking is important, one of the 10 life skills. We see all that. But maybe, that I'm just only taking critical thinking as a key point. But perhaps the definition of it, an easy enough structure of it, and then, introducing that as part of series of acceptable curriculum, eventually everything has to be sort of broken into units and examples and exercises and assessment, sadly, right? So, and then getting a whole bunch of teaching community to accept that is where the challenge is. If you go to anybody and say, do you need critical thinking or not? I think nobody is going to say, no, we don't need critical thinking. Right?
There are two kinds of challenges. One, let me take the simplest challenge possible. Students. It's easy to attract the students and such that they will learn critical thinking from the materials that we produce. That's the simplest part. Okay, so if you begin in schools, that's the best. They will continue doing things on their own when they get into the undergraduate courses and PhD and so on. Changing teachers is harder than changing students. Definitely, because teachers have invested so much time and so on, and teachers do not have the time that students have. So it becomes much harder for teachers. When it comes to the next level, namely administrators, managers, and when it comes to still higher, the decision makers and so on, you will find positive resistance, because critical thinking involves challenging authority, challenging experts, and experts don't like it. So one of the problems that we had in NUS when we had this inquiry-oriented linguistics curriculum was that our students went and challenged the teachers in other subjects. That was not, and the students were, regarded as arrogant people and so on, and we received lots of complaints. So we had to tell our students, look, you cannot behave towards other teachers the way you behave towards us. So when you're attending a lecture, just listen and take down notes. Don't ask questions. They don't like it. And I think students are intelligent enough to understand the difference.
Maybe an older student, Professor, but if it is a younger student, it is so confusing to them. Like, one set of teachers are saying, question everything. And then there are other set of students who are saying, shut up and write it down and go away.
I think
can be quite.
6th grade students know. I have taught 6th grade students. They are smart enough to understand the difference.
Okay.
Yeah. In fact, I will show you a video in which students ask the administration to introduce critical thinking in their curriculum. And then they, one of the problems that they found was that teachers are not ready for it. So students are smart enough. They have a natural inclination. They enjoy this. But by the time you move from 6th grade to the 10th grade to the 12th grade to the undergraduate students, all those mental abilities are beaten out of you. And by the time you get to your PhD, all thinking abilities are systematically destroyed. So this is the tragedy of our education. So instead of doing that, instead of education destroying your thinking abilities, education should nurture those abilities.
Is it a problem only in Indian education system, or do you think it is a problem across the world?
It is all over the world. A few education systems are different. So, for example, the Finnish education is different. By and large, in Nordic countries, the education system is different. In US, some schools have extremely good education. Some rare, and those are typically expensive schools. I've seen those things happening even in neighboring towns. The schools in one town extremely good, and the next town. Typically, what happens is in rich areas, you get extremely good education. In poor areas, you get horrible education. So on the average, for example, in the US, education system is broken. But you also have incredibly good schools and universities. So it is extremely uneven. Okay. By and large, in places like the Nordic countries, it's even. Most schools are good. So but I think by and large, education system all over the world has been aiming at creating administrators. That comes from China. The system of testing was designed to create efficient administrators, supporters for emperors, and soldiers, people who obey you at any cost. So creating administrators and soldiers has been the implicit goals of education, not creating thinkers.
Okay.
Sometimes creating thinkers can be a problem for society, which is why they killed Socrates, and they gave him poison, which is why they burnt Bruno alive, was saying that the earth revolves around the sun. Those things, you have to be careful in avoiding such fates. They can put you in prison. This happened in Stalin's time in Soviet Russia.
Yeah. Dissenters
were punished, whereas the essence of academic thinking is dissent.
Yes.
So we are in two completely different cultures, and we are advocating perhaps a slightly dangerous culture, but you should have the ability to protect yourself. You can dissent in your mind, but whether you dissent openly or not depends upon what the situation is like.
Okay. Okay. I have one more question. Maybe I'm just thinking loud. When I was looking at Indian philosophy, I came across something called Tarkasastra, which I was told was taught to all students of philosophy so that they can have a solid backing in what they are learning. So is that something that we can go back and take a look, or do you have some views on it? Badri and others, you can add to this if you have a point of view.
Tarkasastra, right?
Yeah, Tarkasastra, yes.
Tarkasastra is based on ancient Indian logical systems.
Yes.
There are three ancient Indian logics: the Nyaya logic, the Buddhist logic, and the Jainist logic.
Yeah.
these in comparison with the logical systems of Greece, for example, Aristotelian logic, our systems are far superior.
Okay.
But they have not been fully well, I don't want to go at length about these things. There are some extraordinary things in our systems of logic.
Okay.
But it is important to bring those things into current logical systems.
Okay.
Yeah. So these were systems of logic designed for scientific inquiry and debating, unlike Aristotelian logic, which was restricted to mathematics, only deductive reasoning. Indian logics go way beyond that, to inductive reasoning and debating and so on. But we can't simply teach the ancient systems.
Yes.
We have to take what is good in those things and bring them to the existing stuff. So, for example, one thing that I have always admired is the statement that it is important to see what doesn't exist. It is not enough to see what exists, but also the ability to see what doesn't exist.
Doesn't exist, yeah.
This is crucial in scientific inquiry.
Yeah.
I
think, thanks, but I'm done. Yeah, I'm done.
Thank you, Professor Mohanan. It was quite interesting. Normally our lectures are on a specific scientific idea or a technology idea or mathematical idea, and we have it's more historical or explanatory. This this very topic also comes to what we are trying to do here. Maybe we should really look at not just just present facts, but sort of trigger. I would like to go back and look at how I would like how I can teach somebody about the modern cosmology, what we know about today, or or quantum mechanics, or a certain higher mathematics, in a way which sort of unfolds naturally, where the student himself can, without me giving facts, can find out by way of series of questions, collaborating with other students. It's a challenge. I mean, people who are good at a certain topic may not know exactly how to teach it in the best manner possible. Okay. So maybe it's also a lot of effort that the teachers will have to take to introduce these concepts into the overall, maybe curriculum presentation, teaching. I don't know. I mean, this whole thinking has to change substantially. You've certainly given us a point to think about, ruminate, and then figure out in our own way what we would like to do as science communicators or as teachers. A lot of teachers were very active in the chat box, not only asking questions but also trying to answer each other. I hope more of this can be taken up and spread at school level, where teachers talk to other teachers. At least throw the question. We have no idea what the answer is, but at least take this lecture and then maybe share it, show to others, and even debate. Even present it to the students and say, hey, this is what Professor Mohanan is talking about, and how would you like something like this to be covered? Would be really interesting.
May I add that we have lots and lots of materials, learning materials that make it easier for teachers at our website. There's a huge wealth of stuff, and you can pick stuff from there and use it in our classroom. So this is the kind of advertisement for our website, which gives materials totally free. We
will share that with all of our the mailing list that we have. We shared your the presentation notes already to our people who we have in our mailing list. We'll also add the link to your website and various material that is there, and we'll also talk to various teachers to just go take a look at it and then figure out for themselves how they should look at this. So thank you very much for your enlightening evening session, and that was really wonderful. Thank you from Varahamira Science Forum.
Thank you.